All right, here we go. Good evening, everyone. Welcome to the Minnesota Astronomical Society May 2021 virtual monthly meeting. We have a very full agenda tonight. We have a very special speaker, and that's why I want to just hop right into this. Okay, why doesn't it advance? What am I doing wrong? Am I not?
You got to click on it first and then advance it.
Oh, look at this. So, board members, here is a list of all the board members. I only know of Waltz and Matt I've seen on tonight. I haven't heard Trina yet.
I'm here.
Trina's there. How about Conrad and Gunnar? Okay.
They're not as cool.
If you don't recognize our names, then there are our faces. And because we haven't been together in a while, you probably don't recognize their faces either if you're new. So there's Trina's face. So these are the board members. So treasurer's report. So the MAS is on YouTube. I'm going to repeat this every month just because I think it's important. So if anybody, and I guess this is the wrong audience, if you missed the meeting, it'll be there. But, you know, for the future, if you missed the meeting, it'll be there. It'll be there. If there's anything that you miss as far as the beginners or anything like that, you know, if we've been recording all these virtual meetings and posting them then to the YouTube channel, so they're there. And then everything in the past too. If you want to go backwards and look at something, if you want to go backwards and look at featured speakers, that certainly is something that you can do. So that's where you find us. Lunar Scope program. Anton, are you on tonight? I didn't see your name, but if you're on, open your mic and talk about the Lunar Scope program. Okay, no Anton.
Yep.
Anybody else? Trina? Oh, go ahead.
Yeah, sure. Yes, members can borrow our telescopes. We have 14 of them now. And the access to that is through our website under members, Lunar Scope program. In addition to the 14 telescopes of all types, we have 5 courses on DVD for on astronomy, of course. So far this year, we've loaned out 24 telescopes, and there are about half of them are available now, and the other half, well, they come in at different times. So if you want to borrow a telescope, just go online to the members Lunar Scope program and make a request.
Awesome. Thank you, Anton. Any questions from any members? Any new members have a question about the Lunar Scope program? Please, this is the time to, you have our attention. We certainly would want to answer any questions you have. All right, very good. Moving along. Celestial events before the next meeting. This weekend, new moon weekend, get out. Maybe you can catch some Eta Aquarids. Yeah, that's not me to pronounce that stuff, but get out there, take a look at those. That's cool stuff.
It's like the Aquarids.
It's Eta Aquarids.
Say it.
Aquarids.
Eta Aquarids.
You guys are the best. What would I do without you? And like I said, new moon next Tuesday. I never look at the weather during new moon period, so I have no idea what it's going to be like. Just because I don't want to jinx it. The other thing is Mercury, greatest eastern elongation, means that it is highest in the western sky after sunset. And then there's the full moon. I'm just going to throw in there that it may appear a little brighter and a little bigger. And I don't want to go any farther than that. But the cool part is that we will be on the beginnings of the lunar eclipse as it is setting. It's it's not. I think, what did I look? I looked today. Maximum eclipse is going to occur when it's actually 6 or 7 or 8 degrees below the horizon after it's set. So it's unfortunate. Minnesota's going to miss out this time. You know, we'll get our shot sometime. These lunar eclipses are going to keep happening, so it'll be okay. We'll see another one again soon. But this one, I imagine you'd be able to see a little bit if you can observe before it gets too bright out. It's going to look a little pinkish, but you know, are you going to be able to say that it's pinkish or reddish because it's in the atmosphere, or is it because it's the lunar eclipse? So it's hard to say. And then the next virtual meeting will be June 3rd. That's really, I mean, it's kind of a boring month. I did some searching and there wasn't a whole lot else going on. There's some close moon things with Antares and some of the planets, but you know, most of those are early in the morning, and I know some observers like to go to bed before sunrise. Some of us, like me.
We need a good comet or something.
We do need a good comet, but you know, what can we say? We had a good comet last year.
I would think by the end. I would think by the end of May, though, that Jupiter's getting pretty close to rising. Before midnight. I don't know where it's at. I have to check.
Yeah, I didn't look, but yeah, you might be right. So some results that I got in from Jerry Jones. By the way, Jerry Jones bailed on us. He's not available tonight. So he reported to me the Messier marathon results, and you know, congratulations to all of you that went out there, stuck it out. I know the weather wasn't fantastic, and I know some of those nights were cold, and I saw some of the posts on the forums where there was some big time frost. So, you know, he kind of, you know, got out there, set up his equipment, got 109 out of 110 from Black Mesa in Oklahoma. You know, that's really cool. Go on the forums if you haven't, and check out his video. He made that available after last month's meeting. Take a look at that. That's very, very cool. You know, congratulations to everyone that, you know, you participated, you turned in a log, you got credit, and you're recognized here. Dick Jacobson, I do want to see your rig someday. I want to see how you can one eye on the finder and one eye in the eyepiece. I'd like to see that.
Yeah, Mark, I'm still tinkering with it, but it does seem to work pretty well. I think it helped me in the Messier object location.
What if one of your eyes is bad, and you know, that would be kind of difficult, I think, because one of my eyes is not so good, and one of them is okay. So I don't know. That would be kind of interesting. That's why I'm kind of interested in seeing that. So maybe someday.
Okay, so, I'll bring it along sometime.
Yeah. Congratulations to you all. Good job. Awesome. So let's what's next here? Star parties. ELO has their Spring Astronomy Day on May 15th. And then they have another public star party on the 29th of April. Who edited this slide? I guess it's the 29th of May. I have to talk to my editor about that. Proofreader. And then MAS Beginners Interest Group has a star party at Medcap Field on May 22nd. We'll cover a little more of that later. And then member parties, CGO and LLCC. LLCC, I know that can be a weekend event if you choose. Follow the forums. There's we have some COVID restrictions there, some rules that we have to follow for those people up there. But I don't think it's anything we can't get around or work through. But there are some special instructions. Ken's done a very good job of getting those set up for us. And then CGO, you know, watch the forums. I don't think there's any official on or off on it. It's kind of you watch the weather and, you know, post if you're going. And, you know, I think the board's going to meet. We're going to talk about some some loosening of the of COVID things, and I'll talk about that more in a couple minutes.
Is there like a Virgo Venture or something sometime this month?
I don't know when that is. Would that be now?
Maybe not. Might be June. I don't know.
Might be June. Yeah, June's kind of bright though. So Astronomy Day 2021, at least the spring one. It's at our outreach premier facility, Eagle Lake Observatory, at Baylor Park, out by Norwood Young America. The observatory is going to open at 1 with solar viewing, and there's featured speakers. I talked to Merle this afternoon. He's going to update the website. They actually have filled in some of the spots and some of the topics for the speakers. So, watch. You go get to that through the homepage of our website, and you'll be able to see some things there. There's door prize drawings. There's always a whole bunch of stuff. I've seen the list of stuff being given away. That's going to be awesome. And there's going to be a night sky tour after dark. Probably I guess dark now is after 10 o'clock, but I presume it'll be like 9:30, 10 as soon as you can see stars and constellations. And the really cool part is it's free and it's open to everyone, members, non-members alike. We and I have down there COVID restrictions apply, and that kind of leads me into about COVID. First thing I want to say to all of our members is, help us and help yourself. Go out, get your shot. The governor's big thing this afternoon was, as soon as the state is 70% vaccinated, he's gonna take us off the mask restriction. And so that, I think, is a big step. So if we're all vaccinated, that means we're supposed to be immune. It's not 100%, but at least the chances are significantly reduced. So we as a board, we are aware of the changes. We need to have a quick meeting and discuss what we're going to do. I have a plan to do that. Board members, if you're around, watch our Slack page. That's where we're going to do that. And then public that's here tonight, and the members. If you're wondering what's going on, what we're doing, we're going to update that, and we're going to keep track of that on the homepage and the forums. I have some ideas, and I don't want to put any ideas or talk about any of that right now, but I just want to say we are going to make some changes, and it's going to go through the board first before we initiate that. So stay tuned. Give us, it's only been 7 hours since he talked about that. So give us a few minutes and let us talk about that, and we'll release something. Suresh, are you on? Silence. Okay. So DSIG has another event coming up at Metcalf Field. If it goes as typical, May 22nd, 8 p.m., I believe, would be the start time. And if it happens to be cloudy or predicted to be cloudy that night, and Friday, May 21st looks better, then I believe it'll shift to Friday instead. And the place to watch that is the forums. Suresh is pretty good about sending out emails to keep everybody informed as to which way it's going to go. So that's the best I can do there. I think that's the best we can do there as to which night it's going to happen.
Yeah, we had a really good BSIG last, what was it, 2-3 weekends ago? I can't remember now. But it was really a good night. We had a lot of people. We had a
control unit. The
Sorry?
resistor plug's broken, but I've got my charge wire.
Okay, go ahead, Matt.
Okay, I didn't know what that was. No, I was just going to say we had a really good night. We had a lot of people. One thing about telescopes is there's a natural social distancing. You can't have them right next to each other. So people were really good about going from scope to scope and checking things out, and the moon was out, so we couldn't see much in the way of galaxies, but we did see some good clusters and really good views of the moon. So it was a lot of fun, and got to see some really interesting scopes, some new ones, some old ones, and a lot of fun.
So we have a special message from Brandon Hamill. Brandon, are you on?
Yeah, Mark, can you hear me okay?
Yes, I can. So the floor is yours.
All right. Hey, thanks for letting me speak for just 1 minute here, Mark. So I wanted to make an announcement to everyone to kind of let you know something, that most of my closest friends in Minnesota come from this club right here, the state of Minnesota. And I want to thank all of you, and I really do mean this with sincerity, for helping me grow in this really wonderful hobby that we have. And I know our past president used to say we have one of the premier astronomy clubs in the country. I actually want to take that a step further. I believe we have the absolute best astronomy club in the country, and potentially I may have visited more clubs than anyone else in this group. So I feel like I can say that with some level of authority. But I needed to let all of you know that my wife and I have made the decision. We're going to be moving to Dallas, Texas, but I plan to remain a member of this club, and I hope to see you guys when I come visit and continue to use our various sites. And I want all of you to write something down, if you would, for me. And I want you to write this down. It's Monday, April 8th. Monday, April 8th, the year 2024. The home that I purchased happens to be on the path of totality for the total solar eclipse that will be happening on April 8th, 2024. All of you, and I do mean every single member in this club, will be welcome to come to my house. I intend to have a party probably that week, Saturday or Sunday beforehand. In case it's cloudy, we can go run somewhere to see the sun. But I just wanted to express my thanks to all of you. And please let me know, even though I will no longer be living in Minnesota, if I can assist you in any way. I wanted to wish everybody nothing but best wishes. So thank you very much, Mark.
You're welcome, Brandon. Well, I guess you're not going to go. We're just not going to see you at star parties regularly. If you're still going to be a member, you're going to still hear from me. You're going to hear from other members in the club. So, but good luck, Brandon. Yeah. I have interests in Texas, so you just never know. You might find me on your doorstep with my suitcase going, hey, you got a spare couch? So
I'm imagining how that realtor talk went. Well, it has to be somewhere on this line.
Yeah, I can't imagine. So thank you, Brandon. Thank you, Brandon, for all you do.
Yeah, thanks, Brandon. Miss you.
Yeah, I already missed you. One quick public service announcement for an astrophotography workshop coming up August 7th. And if these COVID rules progress as planned and as projected, we're going to be able to get together, and we're going to be able to get together at ELO in the hotspot classroom. And currently we have a limitation of 25 people, and I think we'll be able to go to our full limitation of 50. We're still hammering out some more details in the background. We're planning a barbecue, of course, which we are going to ask all participants to participate in, or you don't have to participate, but we're going to ask you to help us out with the cost. Those fees are being worked out. We're still plugging away a little bit on the agenda and the plans, but Mike Shaw is all in. We've even talked to him a little bit about doing a on the field type demonstration and talk and stuff like that, kind of not so formal but informal, to get better get to know the possibilities of you and your equipment doing nightscape photography. So we're really looking forward to that. Stay tuned, circle your calendar. We're going to release some things in the next couple of weeks for sure.
Got a hand raised on here from Mark.
Okay, Mark, you want to open your mic and ask your question?
Not so much a question, just a little note for some of them that might be interested in the program. It's not astronomy related, sorry. Just before coming on here, it's got a notice from PBS that they're having Mr. Fujita, the scientist who did major work on tornadoes is on American Experience, Monday, 9 p.m., channel 21.
Thanks, Mark. So as always, I'm putting a call out for Gemini articles. You know, I don't think Father Brown to turn down any article from any member. You know, any kind of astronomy equipment, any kind of troubles and tribulations you've had, book reviews. You know, I think if it fits in the astronomy catalog and it comes from a member, I believe he would take it and he will help you edit it to get it in a good form to be able to publish it. And that you know, I haven't heard from him, so I have to believe that he's getting enough articles. And the last Gemini that I looked at was looked to be pretty full. There's lots of very interesting things. So keep them coming, I guess, is the message I have right now.
Mark, this is Father Brown.
Hi, Father Brown.
I have enough articles for June, but after that, the cupboard is bare. So I really would appreciate members giving, sending me articles. I would have nothing at all for August.
Okay, so there it is. Members, please.
I also have another question or an observation. Anton mentioned the astronomy DVDs of the great courses. I gave about 5 of those to the club, but I hadn't heard anything about them. But I understand that now they are part of the scope of Lunar program, and if so, Anton, if you would be able to give us a list of those, so that people would know what they can borrow for a month. I also have some others, but I stopped donating them because nothing was done with them. So if they are being lent out as part of the Lunar program, that's great, but the members should know what is available.
I can send you a list. That's we've had them up on the website, I think, for months, if not about a year now. And there's been some demand for them. A couple people have really enjoyed them. But yes, I can send you the list.
Yeah, I thought they were listed on the website, so that's.
I see something on the MAS Lunar Scope program page.
Oh, okay.
It does list some titles. I don't know if it's the whole list or what, but definitely it's there.
And Anton, if it's short, if the list isn't complete, please let Volts know, and he'll get that updated for sure.
And also, I do have some other astronomy courses that I could still donate. I would have to look, but there is a list on the webpage.
Yes, there is.
Oh, okay, very good. Thank you.
So I have said since I became president that I would be doing Better Know a Constellation every month, but this month I've been so busy. I didn't prepare anything, but I am asking that if somebody else wants to do that rather than me, please get a hold of me. Please contact me. President at mnastro.org would certainly work. And I probably will have something for June if somebody else doesn't have something. So I just want everybody to know that's, I think this is a great forum to speak about that. And, we all could find something or learn something about a constellation every month. So I think it's would be great if another member would share. Just take a little bit of load off of my shoulders. I'd appreciate it. Thank you. Astronomical League Awards. Jerry Jones bailed on us this month, and he's probably listening silently. He said that he might tap in. So if he is listening, and he was probably laughing. So because I'm giving him a hard time because he bailed on us last month too. So this month he told me that there are 3 awards. They're all 3 the same, honorary Messier awards. I wish he was on so he could explain what these awards are, because I'm not sure. But Trina and Claire and Don, congratulations on this achievement. Maybe someday I'll look this up and see what this is, but I imagine it has something to do with the Messier objects.
Yeah, it's finding all 110 of them and logging them and submitting it to Jerry and the Astronomical League to get our certificate and our pins. So we all get some new bling.
Nice work, everyone. Congratulations. And in the words of Jerry Jones, get out there and observe. Let's get some more awards. Everybody needs more bling. Good job, everyone. What's my next slide? Oh, wow. Look at me. I'm 10 minutes fast. So our next meeting is Thursday, June 3rd, again at 7 o'clock right here. It's going to be virtual again. Featured speaker is going to be Chick Woodward from Minnesota Institute of I can't read that because there's something in my way. The Institute of Astronomy. He's going to talk about comets. I'm kind of excited about that, but you know, it's comets. So that's all I have. Is there anything else anyone has? I see the chat is going crazy. Let me see what's up with the chat. Anybody have anything in there? Oh, no Alex online yet.
If you would like, this is Vault. I have some pictures of a new toy that I just finished, a project that I completed. I don't have a presentation, but I can show a bunch of cool pictures.
Vault, you know what? Let's do that. Let's do that until we see Alex pop on.
All right, I'm gonna have to figure out how to do this.
I stopped sharing.
I am logged in as also the president, so I don't know how to do this. How to share I need to share a web browser here. I don't know how to do it. Oh,
just,
here we go.
If you just share your screen.
I got it. Okay. All right, so I am sharing a web browser with pictures. So does everyone see?
Yep.
Yeah.
So you see an musty old telescope?
Yep.
So about in the beginning of March on Craigslist, a listing for a used telescope, refractor telescope popped up. And I jumped on it right away because it didn't look like one of these Indian manufactured pieces of decorative junk. So I went ahead and got this telescope, and then these are the before pictures. So I really didn't know what I was going to get into, but it turns out it's a 4-inch Messier refractor. So it's all brass. It weighs about 25 pounds. It's a flint forward doublet achromat. So it's actually quite a unique refractor in terms of its optical design. It's about an F10, and it came with some eyepieces and some other stuff. And so I like to build and rebuild this kind of stuff. So I started cleaning it up, and this is just a lot of the before pictures, a lot of the stuff. Started disassembling this guy. You know, it's all brass. It's just solid. Actually, the focuser was manufactured by Warner and Swayze in Cleveland, and based on feedback I got from the Antique Telescope Society guys out east, this is about a circa 1910 refractor. And so these are all the pieces. It's definitely a Messier lens cell, and all the other things. It's a very unique main lens holder.
We've only seen one picture so far.
Really?
Yeah.
Oh, it says it's screen sharing is paused. So hold on, I've been flipping through. Resume share. I'm sorry.
There we go.
All right, so I'll flip back through it. Is it still? Are you seeing different pictures now?
Yes.
Yeah. Yeah,
okay,
we are.
So I'll flip back real quick.
Yeah, go back to the beginning.
Yeah. So as you can see, the lens tube was in very rough shape, but it was pretty solid from and the glass was pretty good. So it's a front forward, flint forward. So the concave element is in the front, which
That's
is kind of
weird.
a unique design.
Yeah.
Some of the eyepieces, some of the finder was broken off, no big deal there. So this is a solid cast focuser holder with mahogany knobs.
Wow.
What is the diameter of that eyepiece holder there?
It's the eyepiece holder. It's an 1.25 inches.
Cool.
It's for 1.25 inch eyepieces. Full thread on cell, solid brass. It weighs a ton. That's the eyepiece holder.
A lot of cleanup.
Lots and lots of cleanup. There's the lens elements. So the out on the left hand side is the flint, and on the right hand side is the other element, is the convex element. So I started cleaning it up. Lots and lots of elbow grease and brasso, and it's getting better and better. That's the inside of the tube. Cleaned up the inside of the tube, re-blackened it.
Wow.
Cleaned up the lens cell, cleaned up the focuser draw tube.
What a beautiful scope, man.
You haven't seen nothing yet. Painted it green.
Ooh.
And there we go.
Oh my.
Looking pretty close to get together. So I was missing a mount. So what I decided to do is design my own mount from scratch. And so first I was looking for a finder, so I bought a cheap brass telescope as a finder, but that really didn't work so well. It's too high magnification, but you get the idea. Cleaned up the lens. The glass is almost perfect.
Were they doing coatings back then?
No coatings.
Oh.
I had to put new air spacers in between the doublets, the elements.
How'd you know? So how'd you know how far apart to space?
Just a lot of discussion with that. I've done this a lot with the Japanese refractors that I've collected over the years.
Okay.
So I just use aluminum tape.
Okay.
Collimated it. Everything's perfect. Now, I was missing a design, a mount. So in SolidWorks, I designed in 3D a full mount for this scope. And then I started building out of red oak, the full mount. Got all the hardware, started assembling everything. And there it is, finished.
Wow.
Wow.
That's beautiful, man.
I had it first light
Beautiful.
2 days ago.
How'd it work?
Fantastic. Not even trying. It split caster without low power eyepiece. So that's when I had it outside. I'm just it's just beautiful, and
You have to get a brass diagonal for it.
I'm looking. I'm looking. Not easy to find.
Question?
Yes.
The swivel mount there, I noticed you use a Lazy Susan on that. But the altitude, did you use any kind of bearings or just a simple friction aspect to that?
No, it's actually they are bronze bushings press fit into this element right here, and then it's a shoulder screw. So
the bronze, is that graphite or an oil impregnated type?
It was just a plain bronze.
Okay, thank you.
So then there's a pressure bolt to keep the Lazy Susan so it doesn't pry it apart too much. And there's the scope. There's more stuff. It's adjustable forward back from the bottom to balance the tube. The tube is 100% balanced. It's balanced pointing anywhere in the sky from horizon to zenith.
Sweet.
Here's a little movie. Before my first light.
This is Father Brown again. That looks like a wonderful article for Gemini.
Yeah, I thought you'd be telling me that. I've already thought about that.
Could you have something for August? That would give you 2 months.
That might be enough time.
Okay, great.
That seems like it might be a good prop at the astronomy day too.
Maybe.
Maybe.
And I believe that's my last picture.
Well done. What a beautiful job and what a beautiful scope. Wow.
I've already had offers for it from the Antique Telescope guys.
Okay, I didn't get your name.
This is Vaults.
Oh, Vault. Okay, great.
All right. Well, thanks for looking at my pictures.
Beautiful.
Terrific, Waltz. Thank you.
If it wasn't for value for the antique, you could probably make about $300 on the brass alone.
I would never do that. Yep. Thank you. All right, Mark. It's all you.
I'm back. I don't have. I'm saving control to turn over to our featured speaker. I don't see him on yet.
You gave him the right link, right?
He's going to join in at 7:45. Is the kind of time that I guide you.
Okay, so 4 minutes. So talk amongst yourselves. Oh wait, that doesn't work very well, does it?
No, not really. So I suppose with Brandon leaving, we should make a pitch to contact Stephen Vick if you're interested in joining the CGO committee. It's hard to do that remote.
What do you mean? He could still be on there.
I know. We can still meet via Zoom.
Anybody have any story? Anybody see anything cool in the last week? Brandon, you've been anywhere? You seen anything?
Well, I will tell you, I had, thanks for asking. One of the more exciting things for me was I was an honorary member of the Fort Worth Astronomical Society, and they asked me to speak at their club last week. And this wasn't finalized. The sale of my house and the purchase of my home all came together basically Wednesday of this week. But I let them know that I was coming, and they kind of thought I was joking when I said, well, I'm an honorary member, but I want to become a real member, although I'm retaining my Minnesota membership. So that was kind of one of the more silly and unique and awkward moments I think maybe I've had in my travels with astronomy. But yeah, guys, our club is thought of very, very highly nationally. And I think when we hosted Alcon a few years ago, I think that really cemented our reputation nationally, that our organization is very, very unique. And it's unique. Obviously, our equipment is unique, and I think that stands by itself as a comment, and we could discuss that at length. But I also think it's the membership and the way that we do things in terms of how outreach-oriented we are and how robust our telescope loaner lending program is compared to most organizations around the country. So again, I just think we have a lot of best practices that we do that we should really be proud of. That's what I would say to you, Mark.
Yeah, and I also know this from some scouting around I've done is, our loaner scope program is free. All it requires is that you're a member, and you can borrow a telescope for a month. So that I know is unique. That is, that's a plus. And I think as long as we continue to maintain that, which I believe we are, it's one of those things. As long as we don't hear a complaint, I believe that it's running fine. That might be the wrong way to look at that, but it's, as a board, if we hear we need parts, we get parts. So that's, we maintain them. We don't just, none of them are junk. So that's, that I think that's a good thing. I mean, as a new member, when I joined 10, 11 years ago, that was a big deal. So, hello, Alex.
Hi there. Can you hear me?
Yes, we can.
Great.
I want to introduce everyone, Alex Filippenko, Dr. Filippenko. He's currently a professor of is it astronomy or astrophysics? I don't have my notes in front of me.
It's both, really, but I guess that's the Department of Astronomy. So I'm a professor of astronomy, but we're all astrophysicists at this point.
Yeah. So I'm going to turn the floor over to you, and you have 90 minutes, and I know you want to open it up for question and answers. I know you want to talk about the interstellar telescopes. That is fascinating in itself. So without further ado,
Well, that's great. Thank you.
Take it over.
Yeah, thank you very much. Am I able to share my
you should
screen
be able
here?
to.
All right, so let me do that now. Let me.
It should be at the bottom of your screen, I believe. There you go. Excellent.
Now,
Awesome.
Be able to. Let's see, slideshow, play from start. Yeah. So I hope you can all see that. Yes.
Yep.
Great. Well, yeah. So thank you for the invitation to speak. You're based in Minneapolis or where?
Yes, we are in Minneapolis. We cover a big space around the Twin Cities, and even out into greater Minnesota. So I mean, it's not just the Twin Cities of Minneapolis and St. Paul.
Yeah.
We go north and south and east and west. So
interesting.
It's an honor to have you. Thank you.
I'll email you a recommended speaker. A relatively new professor at the University of Minnesota, Twin Cities, is Patrick Kelly. He was a postdoc at Berkeley in my group, and he started at University of Minnesota a couple of years ago. He does some really interesting work, and I'd be glad to send you his email address. I hope you can get him as a speaker. He'd be really interesting. So yeah, great. All right. Well, let me give you first an outline of this evening. I hope you had enough time to get your business stuff out of the way. Is that right?
Absolutely. We got all of our business taken care of, and even a little introduction to a really old telescope from 1910.
Oh, cool. Okay. Well, so I'll give you a talk on the accelerating universe and sort of a new surprise we have. And then, I'll have a Q&A. And then I think Brandon asked me for sort of a brief story of how I got to where I was starting as an amateur astronomer, which I did. Okay, so I'll do that. And he had heard stories about how I had met my wife and all that kind of stuff. So I'll just briefly tell you a little bit about my life, not much. And then, although it will still be daytime in California, even at that time, I will do a little virtual stargazing session by showing you some photos I took with my unistellar EV scope. And I don't know if any of you in your group have one of these things, but they're amazing. They have a new version now called the Equinox, I guess, E big Q Equinox. But anyway, it's incredible. So I'll show you some images and talk about them. But I think it's a transformative thing for amateur astronomy. And in fact, is enabling a huge amount of citizen science, because there's now more than 1,000 amateur astronomers monitoring stars for transiting exoplanets and things like that. So if that kind of thing sounds cool to you, you might want to look into getting one of these things. And if you're interested, you can email me. Actually, I'll give it to you at the end of this presentation. I know one of the 4 founders of the company. He used to be a postdoc at Berkeley, and he's given me a deal where if I refer people to their company, you guys get $250 off whoever buys it, and stuff. So anyway, it's an amazing thing, but I thought I'd just do a little star party since I got into astronomy very much from the amateur perspective, and I'm still an amateur at heart, really. Anyway, the formal part of my presentation on the accelerating universe starts with Vesto Schleifer, who's not nearly as well known as he should be. But in 1917, he was looking at the so-called spiral nebulae. They were not known to be external galaxies yet. And, he obtained spectra of them. He passed their light through a prism or reflected it off a grating and produced a spectrum. And he noticed spectral lines that were similar to those in the sun, sodium, neutral sodium, singly ionized calcium. I know some of you might be spectroscopists, because even that is in the realm of amateur astronomy now. It's amazing what CCD technology has done for us and all these go-to telescopes and stuff. But anyway, you notice the same patterns as in our sun, but shifted toward longer wavelengths. This is known as the redshift. And if interpreted as a recession speed, it indicated that most galaxies, most of these spiral nebulae, were moving away from us. The Andromeda Nebula has a blue shift. That's because it's gravitationally bound to us and it's in the same local group. But most of them were moving away. So that was kind of curious. But he didn't know the distances of the spiral nebulae, so he couldn't do much else with this piece of data. Then along came Edwin Hubble, who's much more famous, and he was able to get the distances of these spiral nebulae. In particular, he used the 100-inch Hooker telescope at Mount Wilson Observatory above the LA basin, in particular right over the San Gabriel Valley. When I was in grad school at Caltech, you could see the domes up there on Mount Wilson. But he used the then biggest telescope in the world in the mid-1920s to get exquisite photographs of these spiral nebulae, the biggest and the brightest ones, including the Andromeda Nebula. And here's his really famous photograph where he was looking for novae. These are old stars, but they undergo outbursts because of nuclear burning on their surfaces. And they're weird little stars, white dwarfs, but they basically survive the explosion. Anyway, he was looking for them and he marked a few of them, and this one he marked N. But then he noticed that in previous photographs, that same star was present. And in general, the true novae were not visible before their outbursts. They're much too faint. But this supposed nova was visible before its outburst. And then he watched it for some nights and he saw that it was brightening and fading in a way that was very characteristic of a type of star called a Cepheid variable, named after the prototype. Is it Delta Cephei? I think so. It's one of the stars in Cepheus. And, they have a very recognizable light curve. They brighten quickly and decline more slowly, with a period of between about 1 day and 100 days. So they're not all the same. But it turns out that the ones that are more luminous on average, so you just take the average luminosity here, are also the ones with a longer light curve period. And that had been discovered by Henrietta Leavitt of Harvard in 1912. She looked at the Magellanic Clouds, which are in the southern hemisphere, but Harvard had an observatory, a telescope set up in Chile, I think it was. And she looked at repeated photographs of the large and small Magellanic Cloud, I think mostly the large Magellanic Cloud. And she noticed that the ones that were brighter on average had longer periods. And because the clouds are these external dwarf galaxies and are very far away from us compared to their physical depth, to a good first approximation, all the stars in a given cloud are at the same distance. So the ones that look brighter are also the ones that are more luminous. And so she discovered this period luminosity relationship. Well, that's great. That means that if you find a Cepheid variable and measure its period of the light curve, you know its average luminosity from the Leavitt law, as we now call it. And so then by comparing the apparent brightness on average with the true power or luminosity on average, you could tell how far away it is. And you do this all the time with cars, right? You look at the headlights of a car of known distance, 2 meters away, and you calibrate how bright the headlights appear. And then you look at a car that's more distant, and the headlights look fainter, okay? So your brain is doing the inverse square law, and you determine the distance. Your brain, as a consistency check, also looks at the angular separation between the two headlights. And, you know, that separation is smaller the greater the distance. That gives you a consistency check. That's actually one reason it's harder to judge the distance of a motorcyclist or something, okay? But anyway, cars, stars, it's the same thing. Edwin Hubble found Cepheid variables and the Andromeda Nebula. They were really faint. He determined that they weren't faint because there was a bunch of smog or dust in the way, because then they would have looked a lot redder than their normal colors. Just like the setting sun often looks yellow, orange, or even red, often in California in the late summer and the fall when we have all these terrible wildfires. You know, the sun looks blood red close to the horizon. But he could tell that the Cepheids had their normal colors, and so probably they were dim because of great distances. And that then led to the realization that the Andromeda Nebula was an external galaxy outside of our Milky Way, settling this big debate, in particular epitomized by the debate between Harlow Shapley and Heber Curtis, the great debate of 1925. These were island universes in a sense. Figuratively, humankind's concept of the universe expanded with Hubble's realization in 1923, 24, 25. So that was amazing, okay? Well, with his distance measurements, together with Schleifer's redshifts, Hubble found that the more nearby galaxies are moving away pretty quickly, but the more distant galaxies, which generally look fainter and smaller, this is part of the Virgo cluster, I'm sure many of you have looked at it, they are moving away even faster. In fact, the Virgo cluster is moving away something like 1,200 kilometers per second. So the more distant ones are moving away faster. Here was Hubble's original plot, where his distances in parsecs, a parsec is about 3¼ light years, is plotted against speed. And there's a rough correlation here. I mean, he had to have a lot of faith in interpreting these data. He also did kind of a really rotten thing. Half of his data, that is the speed axis, came from Schleifer's work, but he didn't even reference Schleifer's work. That would be grounds for expulsion, even if a professor has tenure these days. If you use someone else's data and you don't properly attribute it. I don't know how Hubble got away with this, but anyway, he also made the mistake that the units of speed are not kilometers, they're kilometers per second, but whatever. Anyway, there's Hubble's original plot. Definitely not something that's particularly convincing. Let me show you a more modern plot on which I'll expand, pun intended. This is from Type 1a supernovae. I'll tell you about them, but Hubble's original data fall in that little gray corner at lower left there. That's that diagram, okay? Look at our diagram that now goes out to 2 billion light years. And in fact, we've gone much further still. We've gone out to 10 billion light years. That'll be what allows us to trace the expansion history and to figure out that the universe is actually accelerating. But anyway, it is an expanding universe, all right? Hubble was right, despite the fact that the data weren't particularly compelling at the time. Well, Hubble, this is now known as the Hubble law. Hubble was actually preceded by a couple of years by a Belgian priest / astronomer, Georges Lemaitre. And so, in fact, the International Astronomical Union a couple of years ago came to a resolution where they now recommend that astronomers call this the Hubble-Lemaitre law. Although the constant is still called the Hubble constant because Lemaitre didn't actually say what it was. But he did have the relationship, broadly speaking, 2 years before Hubble. Hubble did it in 1929. Lemaitre did it in around 1927. Interesting character. Was a priest, but an astrophysicist as well. Anyway, Hubble himself resisted this interpretation, but we now think that the redshift is what's called a cosmological redshift, produced not by a movement of galaxies through some pre-existing space. So it's not a Doppler shift, but rather it's caused by an expansion of space itself. And things that are tied down, like light bulbs and observatories, and you and Earth, don't expand. And even the space in our solar system doesn't expand because it's held together by the sun's gravity. And our galaxy doesn't expand either because it's held together by all the gravity of the stars and the dark matter and stuff like that. But the space between galaxies, or more correctly, between clusters of galaxies, expands. And the light, the electromagnetic radiation, expands with it. And that, we think, is the fundamental interpretation of the redshift. But going back to this diagram where we're in the Milky Way galaxy and we see nearby galaxies moving away pretty fast, but more distant galaxies moving away more quickly, it looks like there's been this explosion or something, and we're the center, and all these other galaxies don't like us. Do we smell? Is it something we said? Are all those galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant galaxies. A 12-year-old in one of my public talks came up with that joke, but I didn't catch his name, so I can't give proper attribution. When I talk about cosmology in my introductory astronomy class at Berkeley, at Cal, I say, what's the problem? Are we from Stanford or something? Right? Big time rivals. Big time rivals. I'm not sure who's the University of Minnesota's main academic and athletic rival, but you could use that joke with them. Anyway, no. We think no matter which galaxy we happen to be in, all the other galaxies would move away from us. That's what you get with a uniformly expanding universe. You get an apparent motion away from you with a speed that's proportional to distance. And here I have a one-dimensional hypothetical universe where I stretch this rubber hose and all the galaxies are moving away from the orange one And the more distant ones move faster because every bit of rubber stretches. So the more rubber there is to begin with, the more it will stretch. So you naturally get a Hubble law. But I could have been on any of these ping pong balls, assuming either an infinite universe or one that wraps around itself. It doesn't really matter. Hubble's law works in either case. And if you don't like my one-dimensional hypothetical universe, you can go back to the textbook example of an expanding loaf of raisin bread, where the dough is uniformly filled with yeast, and you let it sit for an hour, and let's say it doubles in size. Every raisin thinks that the others are going away from it, thinks that it's the unique center, but none of them is. And each one sees the Hubble law. That is, every little bit of dough expands. So this one moved away at 5 centimeters per hour. This one moved away at 10 centimeters per hour. Okay. And again, it doesn't matter whether I have a finite universe or an infinite universe. Okay, so that's the interpretation of the Hubble expansion. And using today's telescopes, we know pretty well what the Hubble constant is. I'll talk more about it near the end. That's the big surprise. But first, I want to talk about how we expect the constant to not be constant. It should change with time. It's only constant in the sense that we think that at a given time, everywhere in the universe, it has the same value. But it should change with time. And this goes back to Isaac Newton, who famously saw an apple fall from a tree. It probably didn't hit his head. And he wondered whether whatever it is that's causing the apple to fall from the tree toward Earth is the same as, or at least related to, what's causing the moon to remain in orbit around Earth rather than just zooming away. And he, of course, came up with his famous law of universal gravitation and the laws of motion. And indeed, in this way, he united terrestrial phenomena with celestial phenomena. Okay? It was a tour de force. Well, all the galaxies are pulling on all other galaxies. I'm sure you're all familiar with this part of the Hubble deep field or the Hubble ultra deep field. It's like a grain of sand held at arm's length. That's the amount of sky this picture subtends, but it has a couple of thousand galaxies. The point is, all these galaxies are pulling on each other, not just because of the visible matter, but because of the dark matter as well that holds galaxies together. Because, Vera Rubin and later others showed that galaxies would fly apart unless there were additional stuff holding them together. So all these guys should be pulling on each other, slowing down the expansion of the universe. And if the universe is dense enough, then the expansion should slow down, ultimately stop, and then reverse course. So if you were looking at galaxies moving away from you, right around now, you'd be a bit nervous, and then, goodbye, cruel world. The universe would collapse in on you, right? So it may have started with a big bang, but it ends with a big crunch or a gnab gib, which is big bang backwards. A little bit of nerd humor there, okay? But if the universe isn't very dense, then the initial speed of the Big Bang could have exceeded the escape speed. Sort of like if I throw this apple more than at 11 kilometers per second and I neglect air resistance, it'll go away from me forever, albeit at a progressively slower rate because gravity is still acting upon it. But in that case, the universe would expand eternally, becoming ever colder, darker, more dilute, and ending in ice, so to speak, rather than an ending in fire. Well, astronomers would like to know, which will it be? We just want to know. It won't give you a better toaster tomorrow. It won't improve your pacemaker, but it's an interesting question. And the way we can go about solving this is by looking at the expansion history of the universe. If I were to measure the speed of this apple at many different times and see that it's slowing down a lot then I could predict that it'll someday stop and then reverse its motion. If it hasn't been slowing down a lot, then it'll keep on going forever. So we know the current expansion rate, but how do we look back into the past? Well, most of you actually probably already know this. Light travels at a fast but not infinite speed. So you see the sun as it was about 8 1/3 minutes ago. Even the nearest stars are typically tens or hundreds of light years away. Some, like Deneb, are 1,000 or 2,000 light years away. You're seeing them as they were tens, hundreds, or a few thousand years ago. So if you look at galaxies that are a billion light years away and 4 billion light years away, and maybe that little speck there is 9 billion light years away, you're seeing them as they were 1, 4, 9 billion years ago, and encoded in the light in the form of the spectrum, the redshift, okay, is information about how much the universe has expanded during the time of flight. Go back to that animation I showed, okay? But we need to know the distances of these galaxies so that we know how much time we're looking back, the look back time. So how do we do that? Well, Cepheid variables, though powerful stars, 1,000 solar luminosities, typically 100 to 10,000, that's still not luminous enough to be seen billions of light years away. It was good enough for the Andromeda Nebula and a few other spiral nebulae, but not for the ones that we're looking for that are billions of light years away. So you might think you're hosed, but you're not. And the reason is because of my background here. Some stars explode at the end of their lives, becoming millions or even billions of times more powerful than the sun. And these are the source of the heavy elements of which we are made and so on. I'm going to focus more on cosmology on this talk. But these things are really powerful. Here's a galaxy, and there's one star that takes a couple of weeks to brighten and some months to fade. But at its peak, right there, it's the equivalent of a couple of billion normal suns. And that's one star. You know, if our sun were to do this, don't worry, folks, it won't. But sunblock of 50 just wouldn't cut it. You'd need sunblock or supernova block of a few billion to protect yourself. But don't worry, be happy. We pretty much know that that's not what our sun is going to do. But some stars do it. And the ones that are most important for a cosmological purpose are the ones that are called type 1a versus type 2. And what do I mean by that? Well, if you take a supernova and collect the light and spread it out into a spectrum and measure the brightness as a function of wavelength, you've got this thing here. So from blue wavelengths to red and then the near infrared. The type 2s have hydrogen. They come from some very massive, rather heterogeneous stars. Betelgeuse might become a type 2 supernova. We're not sure whether it'll retain its hydrogen envelope or not. But it's definitely not going to be a type 1a, because that comes from a very different type of star, not a red supergiant. But you see, they don't have hydrogen and they don't have helium, the two most abundant elements. So they come from a very weird star, a white dwarf, which is what our sun will turn into. But our sun will not become a type 1a supernova because our sun is a solitary star. But those that are in binary systems that are sufficiently close together that the white dwarf can steal material from the other star, well, if that material piles up and doesn't get blown away by the nova process, and often it does, but in some cases somehow it doesn't, then the white dwarf mass can grow until it reaches an unstable limit called the Chandrasekhar limit, after Subramanian Chandrasekhar, who won the Nobel Prize for this work, I believe, in 1984, 50 years or so after he did it. And these things go off as a thermonuclear bomb, always at the same mass, 1.4 solar masses. So theoretically, they should be pretty uniform in how they explode. And observationally, we see them exploding in nearby galaxies and we see that they're pretty uniform. Not exactly uniform. And, if it were that easy, this would have been done decades ago. But there are ways we can read the label on the light bulb and see if it's a 100-watt light bulb or 84 watts or 115 or what. But they're all pretty uniform. They can also come from merging pairs of white dwarfs. And there you might think they would be not uniform, but the point is that the less massive, bigger white dwarf gets tidally torn apart by tidal forces. Then it forms an accretion disk around the more massive white dwarf. And then that more massive white dwarf grows again to the Chandrasekhar limit and it explodes, okay? So they're pretty uniform. So first we need to find them in galaxies of known distance where we have measured Cepheids or red supergiants or some sort of star, more or less normal star. So we know the distance of this galaxy. Then we find the peak brightness of a type 1a supernova. From the peak brightness and the known distance, that's what allows us to calibrate the luminosity. That's like the car of known distance. Well, how do we do that? I could have each of my students staring through the eyepiece of a telescope looking for a supernova, and then we would let them graduate and move on to greener pastures. But in a typical galaxy, a star might explode every 50 years or something. So this would be cruel and unusual punishment. I can't take advantage of students this way. I can't even make them look at 1,000 galaxies a night, improving their odds, because they have more important things to do, sleeping and studying and partying and things like that. But with today's modern technology, which you even have on your phones, or a little bit more expensive, but not much more expensive, wonderful CCD cameras that amateur astronomers buy right and left now. They're not that expensive. You attach those at the eyepiece end of a telescope, take photographs of thousands of galaxies, and simply look for arrows. Wherever you see an arrow, you see an exploding star. Well, maybe not, okay? I must admit, we put these arrows in with Photoshop or something. We wouldn't give degrees for this kind of work if it were that easy. But what we've done is at Lick Observatory, which I've got here on my t-shirt, owned and operated by the University of California, my team developed a 3/4 meter telescope, which isn't big by today's standards, but it was programmed to look at more than 1,000 galaxies a night. And then it would repeat the process and it would look for differences. So here's an example of a galaxy that looked different, not just because of the arrow, but there's something that wasn't there a few nights earlier. Okay, these are all foreground stars in our own Milky Way galaxy. Don't worry about them. But here's something that looks like it could be real. But it could be a charged particle, a cosmic ray that hit the CCD, or it could be some asteroid flying through Earth, the field of view, hopefully not with Earth's name written on it. It could be other things as well. So out of 1,000 images a night, we have maybe 10 or 20 candidates. And then I have undergraduate students who look at the candidates and use their superior eye-brain combination to evaluate which ones are likely to be genuine supernovae worthy of further consideration. And these students get their hands dirty with research at an early age. Most do not become professors of astrophysics. That's okay. They use their knowledge in, to go on to, applied physics or medical physics, computer science, engineering, things that are more immediately useful to humanity. But they got really jazzed about doing research. They learned all kinds of interesting statistical techniques and stuff by participating in my group. And this fellow here, UK, he just graduated and he gave one of our 2 noontime exit talks today. He's going to grad school next year at Johns Hopkins University. So we would have weekly group meetings where I would buy them pizza and they would justify their existence. Here's one of my grad students. He gave another exit talk today. That was January 2020. You all know what happened in March. So here's one of my group meetings in June. No pizza, sorry. We're just beginning to get together. Tomorrow I'll have it, but most of them are dispersed throughout the world right now. So only I and 2 other students will be there. I'll treat them for pizza, but we're gradually, getting vaccinated, and the campus allows us back if we've been vaccinated. So anyway, I'm very proud of my team. They also conduct observations with the 1 meter telescope at Lick, where we get loads of time so they can learn how to use it and make mistakes and gather their own data and all that kind of stuff. It's really great. They can also help take spectra with the 3 meter telescope at Lick Observatory. So they really get an opportunity to conduct real research as undergraduates and graduate students. And it's great that it's only a 2-hour drive away from our campus and 2 hours from UC Santa Cruz. The other UC campuses are somewhat farther away. But we've also developed techniques whereby at each of the campuses, there are these observing rooms set up with a whole bunch of computer screens, and we have a fast internet connection so they can run the telescopes from their home campuses. And the past year, during shelter in place, we've even developed home observing techniques because we weren't allowed back on campus. So we now are allowed to observe using our laptop computers or whatever from home. So it took a month or so to get that going, but it's really great how students can be so involved now. The campus observing rooms, and now the home observing. So though Lick Observatory doesn't have the biggest telescopes today, we are equipped with modern telescopes and instruments, and there's lots of time for studying repetitive processes like, looking at the light curve, the brightness versus time of a supernova, or searching for exoplanets by getting the Doppler shifts of stars, or by looking at transits or whatever. That's subject of a different talk, but that's the automated planet finder there. There's our Kate thing. There's the 3 meter telescope. So this is really a great observatory for students and postdocs to use. But I just wanted to mention very briefly that the University of California is, like many public universities, I know University of Minnesota is in similar shape. Our financial future is uncertain, especially so in the past year because of COVID-19 and, lost revenues from tuition. I mean, we're public, but we have to still charge some tuition and stuff like that. And the university had to spend money on, installing these HVAC air conditioning systems or filters in our classrooms and stuff for when we open up, we hope in the fall. So anyway, we're in bad shape, and we've been told that Lick Observatory will be cut in funding by 10 to 15%. And we were already kind of a bare bones operation. So through my efforts, Google made a gift of 1.5 million, which we're very grateful for. And we're now raising matching private donations. Either lots of very big gifts or many small ones, or some combination to that, combination of those things. And these gifts can also be used for student and postdoc fellowships, because if we don't make scientific use of the telescopes, then they're not that useful. Also, if we don't continue our public outreach, which the students and postdocs do a lot of as well, we have a lot of visitors each year. So anyway, if you're at all interested in helping us out, you can go to your favorite search engine, look up give.berkeley.edu and put Lick in the search box. And, no contribution is too small, basically. So, thanks for listening to that quick pitch. Or if you if you know someone who wants to make a large contribution, and there may even be naming opportunities for sufficiently large ones, have them contact me. Anyway, so we found a bunch of these nearby ones in galaxies whose distance we know. Then the trick is to find ones that are distant and use them in 2 ways. First, by looking at how bright they appear to be at peak and comparing with how powerful they really are, you can get the distance and hence the look back time. And secondly, if you measure their redshift, well, then you've got the second variable. We needed redshift versus look back time. I might have forgotten to say that, but it's that function that we need to measure in order to determine the expansion history of the universe. It's like the apple that I threw up and I measured its speed as a function of time. So we used telescopes, both teams that did this, primarily in Chile, a 4-meter telescope that has a wide angle camera that would take pictures roughly the size of the full moon, even though I recognize the full moon is not a rectangle. But in this picture, nearly every fuzzy blob is a galaxy. And so this has maybe 1,000 galaxies. So with 50 such photographs, you're measuring 50, maybe even 100,000 galaxies. And if you repeat the process 3 weeks later, some of those galaxies will have produced a type 1a supernova, okay? And you find them by digitally subtracting the earlier images from the later ones. And here's an example of the actual data we used, taken in 1997. And here's the net image, this minus that. And there's a bunch of noise. That's okay. Any measurement process is necessarily associated with some noise. But here, cleverly placed in the middle, is something that looks like it might be real. And a Hubble Space Telescope picture of it a couple of weeks later shows it again, and it's marked with an arrow. So you know it's a supernova. Well, again, not really. Plus, you don't know whether it's a type 1a, and you don't know its redshift. So it turns out my job on both teams, and I was the only person who at one time or another was a member of both teams at different times. I just parted ways because the style, the culture of one team was more to my liking. But anyway, I have access to the world's greatest optical telescopes, the 10-meter telescopes on Mauna Kea volcano in Hawaii. And so I could get spectra of these things because of the supernova candidates, because though really faint, the 10-meter telescopes are just enormous. Here's Fred Chaffee, former director of the Keck Observatory, showing the size of the Keck telescope, you know, one of two compared to with a person. I think across a diagonal is 1.8 meters. So that's a full-sized adult, a typical adult, you know. So these gather a lot of light, and we could get spectra. So again, here's brightness versus wavelength. And here's a low redshift, essentially very nearby type 1a supernova. It has all these features: silicon, neutral silicon, singly ionized calcium. There's some iron and other stuff here, whatever. But here's one whose pattern looks the same, you know, modulo some noise, but these main features look the same. So this is a type 1a supernova with a look back time of around 5 billion years, redshift 0.455. So when we got spectra like this, I was a very happy camper. But the other reason to go to Hawaii, of course, was to use the beaches and stuff. But anyway, so here's the punchline. Here are a couple of Hubble pictures of supernovae that I verified and whose redshifts I got. And the punchline is that they're faint. They're really, really faint. And you might think, well, sure, they're in these scrawny, pathetic looking galaxies. Here, you can't even see the galaxy. Maybe it's that little blob right there, but you can barely see it. Okay, so obviously these guys are going to be faint because they're in these very distant, faint galaxies. And that line of reasoning is correct, but the problem is they're too faint. They're too far away to be in any well-behaved normal universe in which normal gravity is acting. Suppose, by analogy, the universe were 1 second old, and I measure the distance of the apple from my hand after 1 second. Well, it's some distance. But the apple has been slowing down because of Earth's gravity, right? So if I made Earth's gravity less, the apple would decelerate less and it would go a greater distance. Well, if I removed Earth entirely and forgot about the sun and Jupiter and all that, the apple wouldn't slow down at all. And so it would get to an even greater distance. But that's the best you can do, right? In a normal, well-behaved universe. There's either attractive gravity or there isn't. So the apple in a given time can get to some distance. Well, we measured the apples, the supernovae, the galaxies in which they occur, to be at a greater distance than they could possibly have reached in a given amount of time. Now you might say, well, what if the universe is 2 seconds old rather than 1 second? Good try, but that's not the solution, because really the supernovae were too distant to be consistent with their redshift. Doesn't matter what the age of the universe is. To the lay public, not amateur astronomy groups, I simply say the apples were too far away given the age of the universe. But for you, they were farther away than expected based on their redshift. It's the functional relationship between redshift and distance or look back time that looked different from what we expected in any normally behaving universe, okay? In any universe which has gravity that's either attractive or isn't present at all. So, I have this analogy. If it's even farther away, it must have accelerated. It's like there's a rocket attached to the apple and it goes zoop and it accelerates. In that case, it can get to a greater distance, okay, than it would have in a universe that was gravitationally attractive. But an accelerating universe, that sounds crazy. The headline that came out was astronomers see a cosmic anti-gravity force at work. And this is right after a meeting in Los Angeles where I was actually the first person on either team to tell the world, in a sense, about this result. And, we use this term anti-gravity hesitantly because people ask us, can we attach this stuff, whatever it is, to our cars and levitate over San Francisco Bay Area traffic jams or Twin Cities, traffic jams? And the answer is no. It's either a property of space, or if it's some new energy field that's within space, there's so little of it that it only manifests itself over millions of light years of distance. We're never going to harness that. But still, it is an anti-gravity effect. But we were worried that we were wrong. This is still February. By December of that year, 1998, no one had found any obvious problem with what we had done. So the editors of Science magazine proclaimed this to be the single most important discovery in science, in all of the sciences of that year. We were obviously pleased and honored by that. The caricature of Einstein looks surprised, not because he's blowing multiple universes out of a pipe. You might not have known that there are multiple universes and they come from the pipes of theoretical physicists. Well, there might be multiple universes. That's the subject of a different talk. But we don't think that they should accelerate with time. We think they should decelerate. And here it's accelerating, and that's why he's surprised. He's doubly surprised because he has a sheaf of papers under his arm where there's an equation. The Greek letter lambda equals 8 pi g, Newton's constant, times the density of the vacuum. And you might ask, why did your club leaders, the speaker, committee, choose this bozo from Berkeley? We all know that the vacuum is zilch, nothing. There's nothing in it. How can it have a non-zero energy? Well, I'm just the messenger. Einstein was the one who said this. And the reason he came up with this crazy sounding cosmological constant is because in 1917, most physicists and astronomers thought that the universe is static. neither expanding nor collapsing. But even though the nature of the spiral nebulae wasn't yet known, the spirit of this argument would still hold. Our galaxy or our sun would be pulling on everything else. And so, if anything, the universe should be collapsing. And yet it didn't look like it was collapsing. So he came up with the cosmological constant, which corresponds to a vacuum energy that's repulsive. And not only does it act in the opposite direction because it's repulsive, it has exactly the same magnitude to counterbalance attractive gravity. So it's like this apple that I'm holding, and Earth's gravity is trying to pull it down, but my hand is pulling it up. So the net force is 0. May the net force be with you, not may the force be with you. They got it wrong in Star Wars, right? They didn't take freshman physics or something. But anyway, Einstein never liked this because it implied a non-zero and repulsive energy of the vacuum. Moreover, there was no experimental evidence in laboratories on Earth that pointed to it, and it had to be tuned to this very special value. So it seemed ad hoc, didn't seem right. 12 years later, when Hubble discovered the expansion of the universe, the whole physical and philosophical motivation for the cosmological constant disappeared. Einstein renounced it as having been, anecdotally, his biggest blunder. So here he is sad that he ever introduced it, because had he not done so, he could have been famous. He could have predicted that the universe is likely to be in a dynamic state, the way some theorists did. But he could have, been famous. He was. But anyway, what would his reaction be now, the better part of a century later, learning that we resurrected the idea of a repulsive effect, but not to make a static universe, rather one which on large scales accelerates. So in your room, the down arrow dominates, on Earth down, in our solar system down, in our galaxy down, in our local group down. Even in our Virgo supercluster, well, yeah, there it starts getting, there it's a bit closer. But at 10 million light years and above, or certainly by 100 million light years, the up arrow dominates, and this repulsive effect easily dominates at 100 million light years. So the universe accelerates. So the biggest blunder might have been his greatest triumph, the notion of a repulsive effect like this. And his only blunder was in the exact value being tuned to equal that of attractive gravity, just an arithmetic error. So if he were around now to see the evidence, and it comes not just from type 1a supernovae, but from other things as well by now, his reaction might have been a little bit like on the cover of Science magazine. Well, what if this stuff is not the cosmological constant? What if the acceleration is caused by something else? It could be. So we now call whatever it is dark energy, of which the cosmological constant, an actual vacuum energy of space, is one possible, in my opinion, plausible candidate, but not the only candidate. So dark energy is more inclusive. The cosmological constant is a subset. And now using supernovae and other measurements, which I won't have time to talk about because I want to get to the Q&A and also to the new surprise. But we now know that dark energy is roughly 70% of all that there is. Again, not in our solar system. That's mostly normal matter, ordinary matter. But averaged over spheres 1 billion light years in diameter, dark energy is 70%. Dark matter, which holds galaxies and clusters of galaxies together, and we don't know what that is, that's 25%. And the only stuff that we're, comfortable with is the ordinary matter. And the stars and nebulae are actually only 0.5%. That is, the easily visible normal stuff is only 0.5%, it turns out. So, this is not your mother's universe. This is very strange. But it's now pretty much the accepted cosmological model because there's so much evidence for it. And so in 2011, the Nobel Prize in Physics was given to the leaders of the two teams that made the discovery with type 1a supernovae. Saul Perlmutter, the leader of the Supernova Cosmology Project at Berkeley. I was initially a member of his team. Then Brian Schmidt, the leader of the High Redshift Supernova Search Team. He's at the Australian National Observatory. And I'm very proud to say that my former postdoc, Adam Rees, with whom we did the work in the mid to late 90s, he was charged with measuring the brightnesses of the supernovae. So he was the first person on Schmidt's team to realize what the data were telling us. Gerson Goldhaber, the first person on Saul's team, had passed away in 2010. Indeed, the Nobel Committee might have waited till 2011 in order for one of the four principals, so to speak, to pass away, because their rule is that it can't go to more than 3 people, even though there were 50 people on the 2 papers announcing this. But these gentlemen understood that without the rest of us working hard in the trenches, the discovery would not have been recognized. So they invited the rest of us to participate in Nobel Week, and they spent a good fraction of their prize money flying us out and putting us in the hotel and all that. So here we are at the Nobel ceremony, and there's the High Z team right after the awarding of the prize to Schmidt and Rees. Here's the Supernova Cosmology Project. I should have been in that photo, but at that exact time, the team with which I was more closely affiliated, Schmidt's team, was having its celebratory lunch. The week was so busy, turns out there were very few times we could all get together. And at that lunch, my wife, Noelle, revealed her consolation prize for all of us who did not technically win the Nobel Prize. And it was this shirt, Dark Energy is the New Black. And I actually meant to wear that shirt today, but I don't know, I put the Lick shirt on in the morning, and that was appropriate in its own way, but Dark Energy is the New Black. Anyway, some years ago, we got the Breakthrough Prize in Fundamental Physics, and that went to all of the participants, which was really great. But again, it's not the prizes, really. The real prize was participating in this discovery. Never as a kid, which I'll tell you about in a few minutes, did I dream that I would be involved in such an important discovery. The best you can reasonably hope for as a scientist is that you'll contribute in some small way to humankind's understanding of nature, and you'll have fun doing it. And if something like this falls in your lap, well, that's unbelievable, you know. Never, I mean, I still have to pinch myself that I was part of all this. And unless there's something we haven't yet discovered and the pie is even bigger than we thought, no one will ever find a bigger part of the pie, right? Of course, it could happen. Before 1998, we only knew of dark matter and normal matter, so that was the whole pie. Well, the final part of the formal talk leads to the surprise. Is dark energy really this cosmological constant, or is it something else? There are things called quintessence and K-essence and all kinds of other crazy things. So one way to figure out, and the data up to now have been consistent, but we're still not sure, is to trace the expansion history more accurately. So these curves in the past have slight differences, potentially, that can lead to very big differences for the future. The current dark energy might become attractive. It could change sign for all we know. We don't know what it is. So what if it becomes gravitationally attractive? If that happens and there's enough of it, we could still have the big crunch. Or suppose it gets stronger per unit volume. Then eventually galaxies will get torn apart. Planetary systems will get torn apart. Stars, planets, and even the atoms of which you're made will get ripped apart. So we call that the Big Rip. Or it could be constant dark energy, constant per unit volume, like the cosmological constant, in which case the universe will continue accelerating faster and faster. but at least clusters of galaxies and things like that won't get torn apart. So, to figure out what the universe is likely to do, we want to more accurately trace this expansion history. And whoever drew this exaggerated for illustrative purposes the differences in these curves. They're much more subtle than this. So what we've been trying to do with Adam Rees as the principal investigator is measure the current expansion rate really well, better than ever before, and compare it with the past. And here's the surprise. The current rate of expansion is higher than expected. Now, you might say, didn't we figure that out 23 years ago? We did. It was higher than expected. But here it's higher still. Compared to what? Well, using radio observations, microwaves, the Planck satellite and others have observed the afterglow of the Big Bang, the cosmic microwave background radiation. And again, that's subject for a different talk, but suffice it to say that all these little freckles are variations of a few parts per 100,000 up to a part per 10,000 in the temperature and hence the density of the early universe. And these are the sorts of things that grew into clusters of galaxies and superclusters and voids. And by using these measurements and the standard model under the assumption that the dark energy is the cosmological constant, the microwave background astrophysicists, of which University of Minnesota has some very prominent ones, by the way, predicted the current value of the Hubble constant. And their prediction, with incredibly small uncertainties, was 67.4 plus or minus 0.5 kilometers per second per megaparsec. You don't even have to worry about the units if they bother you. Before our work, the previous direct measurements were somewhere in the range 70 to 75, with an uncertainty that itself was uncertain, 4 to 7 kilometers per second per megaparsec. So, 70 minus 4 is 66, and that's sort of consistent with this. And 75 minus 7 is 68, so that's sort of consistent with this. So, there's a possible conflict here, but the error bars are large and they overlap. I mean, the values overlap because of the error bars, and the error bars themselves are uncertain. So what we decided to do was to measure the current expansion rate, Hubble's constant, with type 1a supernovae in sort of a two-pronged approach. We measure them with the Hubble Space Telescope and with the Keck telescopes. And we measure their light curves with the Lick telescopes, by the way. And we choose then nearby type 1as that appear in spiral galaxies that show in Hubble pictures Cepheid variables. Okay, there they are. They're circled. And by getting multiple pictures with Hubble, we can tell that all those circled things are Cepheid variables. So we've been measuring the distances of type 1a supernova host galaxies, better than ever before. And over the past 10 to 15 years, we've been publishing our results, and they've become stronger and stronger with time. Our most recent result, about to be superseded with a paper that we're working on that'll come out sometime in 2022. I can't tell you the answer yet, both because we don't yet know the answer and because it would be embargoed, but the latest published value is 73.2 plus or minus 1.3. The Planck satellite says 67.4. There's now a conflict at more than 4 standard deviations. And indeed, if you take into account other data other than our own, it's more than 5 standard deviations, which means there's only a chance in 2 million that it's a statistical fluke that isn't telling us something interesting about nature, about the universe. So as we've been publishing values whose uncertainties decrease, cosmologists have been taking greater and greater notice of our results. Oh, and by the way, if you believe our result, the age of the universe is only 12.8 billion years rather than the usual 13.8 that you read about in the press, and that even I tell my students about in class, because that's based on the Planck satellite. But if you believe that the Hubble constant is faster, that means the universe got to be its present size in a smaller amount of time, basically only 12.8 billion years. But if you put all the different methods together, the tension now, that is this disagreement, the tension exceeds 5 standard deviations. All the late time measurements, the present day universe measurements, together give sort of 73 plus or minus 1. And the measurements that are in one way or another linked to the microwave background radiation give, 67.4 plus or minus 0.5. So what the heck is going on? Well, it's still possible that the early or late results are wrong. We hope that's not the problem. That would be the boring, result. But again, now there's many late time results, and there's at least a few ways of doing this. They're all tied to the microwave background, so they're not totally independent, but still they're somewhat independent. And, so it's looking less and less likely that either the microwave background people or the today's universe people are wrong. So let's suppose they're right. So what could possibly be going on? Well, could general relativity be wrong? Maybe, but we're pretty hesitant to come to that conclusion just because general relativity works so well. GPS is based on it, and there's been so many tests, the gravitational wave detectors from 2015, fantastic. And general relativity just has such a beautiful and simple physical and mathematical framework. So we're really reluctant to get rid of general relativity, but it's possible. There might be a non-zero curvature of the universe. We think it's flat, that is, big enough triangles satisfy Euclidean geometry, but maybe it's not. Maybe it's curved. That could lead to this result. Maybe we're in a large, low-density bubble, which leads to a locally bigger expansion rate than the global one. But the data don't seem to be consistent with that. So I don't think so, but it's still possible. Maybe dark matter, which I said, we don't know what that is either. Maybe it's behaving weirdly, affecting either light or some of our measurements. I don't know. Maybe dark energy is becoming stronger and we're going to get ripped apart. I don't think so, at least not to this degree, because there's other data that argue against the big rip, but I don't know, maybe. Maybe there was an early form of dark energy that gave the universe a boost. It's like you're watching a kid's soccer game and you see the ball zipping by you faster than any one kid could have kicked it. Well, one natural conclusion is that some other kid kicked it first, and then a second kid kicked it, and that's why it's going so fast, okay? So that, I think, is more reasonable. I think that could be a solution. Or maybe there's a new, very light subatomic particle, some form of neutrino or something. We call it dark radiation. It's not radiation like light, but it's traveling at nearly the speed of light. It's very rapidly moving particle, but not dark matter and not dark energy. So dark radiation, that would change the early time expansion of the universe. And if it's not taken into account in the standard model, obviously then the extrapolation of the early time measurements to today would give the wrong answer if you're not taking into account something important, right? So that's sort of my favorite, although I think the early dark energy might be becoming my favorite, just because my particle physics friends tell me that there are pretty good reasons for thinking that that's not the case. So I don't know. So, who knows? But stay tuned. This is really becoming a major league cosmological conundrum. There are more and more articles in the press that are discussing this because more and more cosmologists are taking note. But, you know, in the end, I can't tell you how the universe will end. We don't know. This article that was written about our work 20 years ago made sort of a statement how the universe will end, as though we're going to tell you. Now with 20 years more work, we still don't know. And so we should have had a question mark here. How will the universe end? You know, if you want to look at galaxies with your very own eyes, and you've all done it, right? But when you're allowed to meet as a group, maybe you are in small subsets already, look through your telescopes at galaxies sooner rather than later, because in the next few tens of billions of years, those galaxies will have been whisked away if the cosmological constant is what dominates the universe. But it's still conceivable that the dark energy will change sign, and there might then be the collapse and ending in fire rather than ice. And Robert Frost couldn't have known about these two possibilities when he wrote his famous poem, Fire and Ice. But it's strangely appropriate for the subject of this talk. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Robert Frost would prefer an ending in fire, a passionate, compressed, big crunch universe. But if the universe and he had to perish twice, then eternal expansion and an ending in ice would be okay with him. And that's perhaps appropriate given his name, Robert Frost. So that's the end of the talk. I'm sorry it went longer than I meant it to, and I'll be happy to stay longer than 9:15 your time, maybe till 9:30, so we have time for the star party. I gave you more details than I normally do because I know that, you know, it's the nature of your group. You already know a lot of this stuff, but let me do a few minutes of questions, and I'll just tell you a little bit about my early upbringing, and then we'll do the virtual star party. And then we'll have more time for questions, either on the talk or on the star party. But let me at least take a few, and I can have the chat room here. Yeah, a sterile neutrino. Ashley said, yeah, a sterile neutrino. What Ashley means is that we know sort of that there should be only 3 forms of neutrinos because Big Bang nucleosynthesis predicts the different isotopes of hydrogen and helium and how much of each there should be now. And that agrees with current measurements pretty well. So there can't be a 4th flavor of neutrino, at least not one that participates in the early primordial nucleosynthesis, because that would mess that up. Let's see. Struggle with 2 different ideas about redshift. You mean Doppler effect and the cosmological one, right? Yeah.
Yeah, I'll just jump in. Exactly that.
Yeah.
You know.
Well, so let me tell you, since you're a special group, that there are a few astrophysicists that do not subscribe to the expansion of space concept. They say that mathematically, you can treat it as a whole bunch of Doppler shifts. The trouble with that is that it doesn't fall within the framework of general relativity and cosmology overall. It's a little bit like, you know, you can do general relativity by doing special relativity at a whole bunch of incremental time steps. Constant velocity, then the next time increment, another constant velocity, then another time increment later, yet another constant velocity. You can add up a whole bunch of Doppler shifts. But the great thing about general relativity is that it's a theory of gravity that replaces gravity with accelerations. It was Einstein's happiest thought, the principle of equivalence, and that then leads to a so much more unified and whole view of nature of the universe. But you're right that, and I've had these arguments with my colleagues, okay, that there is a way mathematically of just treating them as Doppler shifts. But by far the majority of cosmologists, including myself, think of it more as an expansion of space. But that's a pretty harebrained idea too, you know, hard to wrap your head around. Yeah, you know, Mount Wilson, I did my early work at Mount Wilson as a grad student at Caltech. The fire got very close to Mount Wilson in 2020. And also earlier in the year, it got close to Lick Observatory. We nearly burned down. The night of August 19th and 20th, I was up all night watching a webcam, in particular, a webcam that was pointing toward my Kate telescope. I thought it would burn down, but then it didn't, it turns out. Let's see here. Whenever science writers refer to dark energy, they use vague words, 3/4 of the content of the universe. Yeah, as the universe expands, the content increases, right? Is the universe becoming more? Great question, Michael. Continuous creation. So here's the deal. Dark energy, if it's the cosmological constant, there's the same amount per unit volume. As the volume grows, there is a greater and greater total amount of stuff. So how is that balanced? I'll give you two answers. The first is that in general relativity, energy is not necessarily conserved, it turns out. So in fact, you can create something out of nothing. Again, if you look at physics.org forums and stuff, there's a lot of discussions of this. I agree with my theoretical colleagues who say that. Nevertheless, if you accept energy conservation in relativity, there's a much simpler and more overall self-consistent explanation. That is that when I raise an apple, I give it potential energy. I've done work on it. As it falls, it gains 1, 2, 3, 4, 5 units of kinetic energy, but it also gains or loses, depending on how you want to look at it, negative 1, 2, 3, 4, 5 units of potential energy. So the sum is 0. So it turns out that this extra stuff that's being created, it has a repulsive effect on the universe as a whole. That's because of something called its negative pressure. We're getting really into the weeds here, sorry. But it also has an E = mc squared like equivalent mass, and thus a gravitational potential energy that's negative. And when you add the negative to the positive, you get 0. Indeed, many of us think that this is how our universe started. Alan Guth at MIT likes to call it the ultimate free lunch, because inflation, which sounds a lot like dark energy, makes a giant universe out of a little one. But that giant universe is a universe with essentially 0 energy. Maybe a little bit starting from the original quantum fluctuation or whatever got this whole damn thing started, okay? But and by the way, a universe where your existence is balanced by your negative energy, the gravitational potential energy associated with you attracting everything else in the visible universe, okay? So you used to be the stuff that contributed to the Big Bang. And anyway, the current dark energy is the same way. By the way, someone said it was Palomar as well. Yeah, Palomar had a fire very close by too, but not as close as Mount Wilson and as Lick Observatory. The arrows are a real giveaway, thank you. Let's see, I'm looking at other things. Perhaps those galaxies don't like voyeurs. I like that, yeah. Milton Humison. Oh, he was born in Dodge Center, Minnesota. Yeah, he was a former mule driver. And it turns out he ended up getting married, I believe, to Edwin Hubble's daughter, right? You can look that up, but he got married, or no, maybe he did, but he certainly became Edwin Hubble's assistant. And in 1931, they published a paper together which showed the Hubble diagram much, much more clearly than Edwin Hubble's 1939 plot. But he definitely was Hubble's assistant, and someone can look up on Wikipedia or something whether he married Hubble's daughter. I might be thinking about Harold Weaver, a former professor in our department who married his thesis advisor's daughter. I might be getting them mixed up right now. Hubble hedged his conclusions because he didn't really believe in the expanding universe. You're exactly right, Suresh. He would say apparent recession velocities. Oh, and Hubble was from Kansas. It was the British accent. Yeah, he was a wrestler and a Rhodes Scholar as well. They should have given the Nobel Prize to him. He campaigned for it, by the way. So should Leavitt. So should Vera Rubin. Yeah, you've read about the EV scope. I'll show you in a few minutes what it does. A couple more questions down here. Will the 30-meter telescope get built? I don't know. There are a lot of political issues with Mauna Kea. It's very sensitive. It's a sacred ground for at least some fraction of Native Hawaiians. We've existed in harmony, relative harmony for decades. I believe we could have continued to exist this way, but it's become a flashpoint for a much deeper issue, and that is sovereignty. Most Hawaiians don't want this, but a few of the more vocal ones don't want to be part of the US. Forget about losing educational benefits and medical benefits and social security and all that. And they're not of any unified mind about how they would govern themselves even. But like it or not, their movement has gained tremendous momentum, often from celebrities who don't even know the details, like The Rock Johnson, I think, is one of the, and Michael says most Native Hawaiians want the 30-meter to be built. Michael, I agree with you up until maybe recently, but there's been so much negative publicity that I think the more recent polls may have indicated that it's 50-50 or even a minority now. But you're certainly right as of a few years ago. So it's just a sad situation, in my own opinion. The Polynesians got there by being amazing celestial navigators, and King Kamehameha was very much for astronomy, and astronomy brings prestige and jobs and education and tourists to the Hawaiian Islands. But we're now very seriously looking at the Canary Islands as a backup. My personal feelings about Arecibo. It was great for 60 years. I myself am not a radio astronomer, but it served its purpose really well. It was an amazing telescope, and we knew it was on its last legs, right? Its cables were fraying and stuff, and engineers were in the process of figuring out a way to bring it down safely. And then one night it collapsed, Yeah. Suresh says, if the universe is now 12.8 billion years, don't we estimate some globular clusters to be more than 13? Yeah, see, I knew this was a great group. Suresh, you're right. But the globular cluster ages have an uncertainty of about 1 billion years. So if you bring that down to 12 billion, then 12.8 minus 0.8, 800 million years is plenty of time for the globular clusters to have formed. Back in the early to mid 1990s, where some astronomers thought the Hubble constant was more like 80 or 82, and they thought we live in an asymptotically flat and asymptotically escape velocity universe. Turns out that universe is 2/3 of the age that you would calculate just using a simple reciprocal of the Hubble constant. So 2/3 of 12 billion was 8 billion. And that was really bad. Plus, back in the early 1990s, I think globular cluster ages were thought to be more like 14 or 15 billion years. So it was much more of a controversy back then. It's not so much now. Let me now show you. Let's see. Let me just go to a different part of my slide deck here, because I know that it's late there, and some people might be wanting to go to sleep or whatever. But let me just tell you a little bit about my history, and then I'll do the star party. And then, like I said, I'll be happy to answer some more questions. But I was always a science nut from my earliest recollections. In particular, magnetism was really interesting to me. But from age 10 through 17, chemistry was actually my main thing. And I entered college as a chemistry major. And I did all kinds of experiments in high school and stuff, blowing things up. Here I am as a senior, president of the science club, blowing up some flash powder or something. But as a freshman in high school, my parents gave me a 2.4-inch refractor as a gift. And that night, I didn't know anything, but I pointed at a bright star, and that looked even brighter. And so that was kind of a thrill, my first view through a telescope. And then I looked at another star, and it looked brighter too. But the novelty was beginning to wear off because, stars are unresolved even through telescopes. And so I thought, well, the next day or whenever, I'll go to the library. There wasn't the internet. This is a long time ago. I'll find out where the good things are, and I'll use my telescope again. But before putting away the telescope that night, I pointed to a third random bright star, let the vibrations settle down, and I realized I was looking at Saturn. So that knocked my socks off, because that night I discovered Saturn on my own. Didn't matter that millions of people had seen it before. That night, no one told me to point at that star. I did it myself, and it wasn't a brilliant discovery, but I thought, wow, if the thrill of discovery can be that great when you find something that everyone and their grandmother already knows about, how truly thrilling must it be to really discover something new or understand something new about nature for the first time in humanity. So that affirmed my intention to go on into science. It was still chemistry, but as president of the science club, or a member at that time, I was only a freshman, I formed an astronomy group, and my interest in amateur astronomy increased. Oh, and by the way, of course, my picture wasn't like a Cassini or whatever picture, but it didn't matter. It was great. All right. So then I joined the Santa Barbara Astronomy Club. I lived in a suburb of Santa Barbara. I think they later renamed themselves the Santa Barbara Astronomical Unit. I got this from their website today. They appear to be quite active still. There's their May 2021 newsletter. They've been having Zoom meetings and stuff too. So anyway, I joined that club, much like yours. That gave me access to monthly meetings. Sometimes they would have professional astronomers and sometimes just members of their organization who researched a topic. And they had star parties in the local mountains at a big parking lot that was like a gun club, okay? People would shoot there at clay pigeons, but they let us use it at night. And so some of the members had some really big scopes. I don't think Dobsonians existed yet. This was like 1972 or 73. Maybe Dobbs did, but I don't remember them. But anyway, there were some big scopes, and so that increased my interest. And then what happened was I entered college at UC Santa Barbara as a chemistry major. But in my freshman year, a couple of things happened. I took an astronomy course from Stan Peele, who was just really a major inspiration. And he taught me that by studying astrophysics, I could have the very small and the very large. So I could have it all. And he taught out of George A. Bell's famous book. He was a professor at UCLA. And Comet West came along, which was really amazing in 1976. And also I blew myself up one too many times. I almost lost my eyesight, but I used to wear glasses and stuff. So I thought, if for no reason other than a sense of self-preservation, I better get out of this field, chemistry. And I switched to physics at the end of my freshman year. and have never looked back. I mean, I still like chemistry, but it's been astrophysics since then all the way. The other thing that influenced me was that I went with Stan Peele to see my first total solar eclipse as a senior in college. We went to the Dalles, Oregon, in the Cascade Mountains. It was raining and totally cloudy while we were driving there. But miraculously, like an hour before totality, the clouds started clearing away. There you can see an overexposed image of the partially eclipsed sun. There you can still see some clouds and scattering off of the clouds. And at the first diamond ring effect, the last cloud cleared away. And our views of totality were just wonderful. And this had an amazing effect on me. I remember visiting my parents shortly thereafter and crying, physically crying, as I described the phenomenon to them. Now, as many of you know, on August 21st, 2017, the path of totality went either through parts of Minnesota or very nearby. I don't remember. I went to Oregon, but I'm sure many of you saw it because it went right through the US. Did it go through Minnesota? It did not.
It was Eastern Dakotas.
Yeah, but very close. And yeah, okay. So I'm sure many of you drove to see it, but I got a great view in Oregon. And if you didn't see that one in 2017, your next great opportunity is April 8th, 2024. Almost goes through Minnesota, but again, it misses to some degree. In fact, here you guys are. Actually, it misses, well, it misses by less than me. I'm way over here. And I'm probably going to go to Texas somewhere because the weather is more likely to be good. But look, you're only, what, I don't know, 500 or 700 miles away. So go see it. So they're really amazing things. Deanne says Nebraska, Wyoming, Missouri. Right. Michael says they drove out and saw it. Yeah, so they're just really mind-blowing experiences. So I urge you all to do it. Dallas. Oh wow, you're relocated, Brandon. Yeah, it goes right over Dallas.
How goes lucky right can you get? Home. I'm not. Come see me, Alex. I'm not kidding.
Look at that. Look at that. I mean, if you go to the center line, it's longer, but it's only slightly shorter in Dallas because you can go quite far from the center line and still have nearly the full duration. It's a very interesting function. It dives near the edges, but Dallas, yeah, that's great. Minnesota was very empty of amateur astronomers that day. Yeah, I hope you got to a place with good weather. I know that as you went farther east, it was much more touch and go. I even know people in the Carolinas, some of whom saw it, some of whom didn't, in Tennessee and stuff too. And Kentucky, it was sort of touch and go, but I hope most of you saw it. You can say in the chat. Wyoming, yeah, Grand Tetons, Jackson Hole. I know I had some friends there. The threat of light pollution, yeah, it's kind of crappy, but that's the way it goes. But let me just tell you, in the last 15 minutes here, I guess I forgot. Yeah, I was asked how I met my wife. So I attended many years went by and I attended the Astronomical Society of the Pacific summer meeting in Pasadena, California. I was actually president-elect. And that's where I met my future wife, Noelle, who was she was an assistant there. She was just helping out. And again, this is their current website. They're not just for the Pacific. You can be anywhere in the world. I encourage you to join. Anyway, we got engaged and married. We were supposed to get married on a cruise ship during the 2005 hybrid eclipse in the South Pacific, but it turns out it wouldn't have been legal by US standards. But she attended that meeting in Pasadena because she used to live in Hawaii. And when she'd come back from her restaurant job or whatever to the parking lot at 9 o'clock in the evening, over the course of the months, she saw the position of Orion changing with time. And so she got interested in the explanation for that. And that's what drove her to not even amateur, just a layperson interest in astronomy. She's never, well, she's had a telescope. So no, yeah, amateur, lay, public type thing. But anyway, that's what drove her to that meeting. And had she not done that and watched Orion, we wouldn't have met. So we decided to name our son Orion after the constellation. The other thing is that we wanted to go to Egypt, the northwest corner of Egypt for the March 29th, 2006 total solar eclipse. But, you know, she got pregnant and here I am, an astrophysicist, and I can't add or subtract 9 months correctly. So we missed that trip, but that's okay. Our daughter was born, and despite, in honor of the really great corona that people saw, this is using just one exposure and then, using this technique where you can combine lots of exposures. What a gorgeous corona. So we decided to give one of the middle names to our daughter, Corona. She was born a couple of days late on April 2nd, but still we couldn't take a trip to Egypt. So anyway, both of our kids have part of their names that's an astronomical theme. Anyway, so that's Brandon. I hope, Brandon in particular, I think was interested in a little bit of my history and how I got in through amateur astronomy and even met my wife through amateur astronomy. And then the thing I wanted to show you a little bit was this unistellar EV scope. It's now been replaced by the Equinox. They're the same, but without an eyepiece, which is really unnecessary, it turns out. There's a CMOS detector down here, which stores up the image. And you can see it through the eyepiece, but you can also see it on your iPhone. And you can have a Zoom session and share your iPhone screen with people throughout the world and have a star party in real time. Oh, and meanwhile, even if you don't want to share your screen, you could be on the top of Mount Everest, and it's a direct Wi-Fi connection from your Android or iPhone to the scope that runs it, okay? You don't need an internet connection. It's just a phone to scope connection that runs it. The image appears on your phone and then you can share the screen. And if you have other people standing around, you can, 10 people can be sort of innocent bystanders looking at their own screen and one operates the telescope. But you can do a Zoom session with Verizon or AT&T. And so that's how I've been doing it for my classes at Berkeley during this time. And I got the university actually to spring the cost because I could do star parties. It's not cheap, it's $3,000, although I have a 8% discount if you're interested. But it's a game changer because of all these citizen scientists now doing all these measurements of exoplanet transits and stuff, and you add all the data together and they're doing real science, or they're monitoring the shapes of comets. I haven't done any of that. I've just done it for star parties. And so let me just show you a couple of images. Here I am, by the way, looking at the Jupiter, the Jupiter-Saturn conjunction in December on my way back from skiing at Lake Tahoe. So here's the moon. The field of view is almost exactly half a degree. It's actually a little bit more in the horizontal direction than the vertical direction. When you save the images, it gives you a circular image for reasons I don't understand. Maybe it's because it's trying to make you think that you're looking through an eyepiece, but when you do look through the eyepiece, it's actually a rectangular. Actually, when you look through the eyepiece, it's a circular image. And on your iPhone, though, it's a rectangular image. And so you get a little bit more area. So it more than fills the moon in one dimension, but not quite in the other. But anyway, here we are just a bit past first quarter. Here's the crescent. And as you know, the Orion Nebula is in the Sword of Orion. So here's an exposure. Shows the colors because every pixel has RGB subpixels. And I think there's one R two G's and a B, and that's meant to approximate your eye's response. And this is really bright, so you didn't need a long exposure on this. In real time, this is what you see. So you can see the trapezium, which here in this picture is a little bit overexposed, but you can see the inner parts of the Orion Nebula. And the colors, the red is caused by hydrogen gas that's neutral, and the electron is jumping from the third energy level to the second energy level. The green color is caused by doubly ionized oxygen atoms, and the blue is produced by singly ionized oxygen. So here you see the colors, and I would explain all this to my students. I'm going a bit fast here because of the lateness of the hour, but there it is with a longer exposure. And you can see the dust nebulae and all that kind of stuff. Now here's a star cluster. You can see there's a lot of red giants. Those are the stars that are more easily visible because they're 100 times brighter than main sequence stars. The centers are saturated, so you get just white, but near the edges, if you zoom in, you'll see the orange color. Here's another open cluster. Here's the Dumbbell Nebula in Vulpecula. And there's the central dying star. You can see that it's sort of bluish in color. That's because it's really hot. The outer atmosphere has been gently burped away in a cosmic burp rather than a supernova explosion. That reveals inner, hotter layers of the star that then emit ultraviolet radiation that ionizes the expanding burped out gas. And the inner regions are bluish green because of singly and doubly ionized oxygen. And the outer parts are red because of neutral hydrogen. And if you squint, and by the way, at this point, you might want to be in a darkened room. You can see these images better in a darkened room, but you can even see the part along the equator of presumably this rotating star where there's denser, fainter surface brightness gas. And I have a thing here blocking my thing, but yeah, this was 100 seconds, okay? But in real time, you can see the image building up. It's just fantastic. It updates every 4 seconds. So that's a planetary nebula. Here's another one, the Ring Nebula. There you can see the central star, just barely, though it's a lot fainter than in the Dumbbell Nebula. But again, you can see the red hydrogen emission on the outside and the oxygen on the inside. Oh, here it is zoomed in a little bit. I might be able to do a bit better if I take greater pains to focus the telescope. These are pretty good images, but they're not the best that I've seen. Here's the Blue Oyster Nebula. I didn't even know about this one before playing with the EV scope, but a friend of mine who bought one said, hey, have you looked at the Blue Oyster Nebula? So I looked at it and it's beautiful. It's got a very easily visible central star and a bluish green expanding shell. So there it is, the Blue Oyster Nebula. I'd never even looked at this, to my knowledge, through any telescope. Here's the Crab Nebula, which many of you know is a pretty hard object to see any detail in, even through fairly large telescopes like a C14 or something. But here you can see, this is a Kitt Peak National Observatory picture showing the pulsar, and it's close to that other star. In my picture, it's this little appendage sticking out from the brighter star. My resolution isn't quite good enough, and my seeing wasn't quite good enough, right? These are actually two fairly closely spaced stars. But there it is. There's the pulsar, the little appendage to that brighter star next to it. I mean, at its peak, the pulsar at optical wavelengths is the same, but its duty cycle is only, 10%. So most of the time it's faint. And so the average brightness is a lot less, and that's what I'm getting here. But there it is. That's kind of cool. Here's a globular cluster, M3. And, there's a half a million stars there. But you're seeing the red giants. You're seeing only the few hundred brightest ones. And you can see these guys look orange. compared to, I mean, going back to the Blue Oyster Nebula, look at that. That's a very blue star compared to that orange star, right? You can see the colors here, I hope. Here you can see that most of these are orange. That's because you're seeing the red giants when you're looking at a globular cluster. The main sequence stars are too faint, by and large. That's pretty good. There it is, zoomed in. Oh, and the way to zoom, you just pinch out on your phone, the usual way. And yeah, so that's kind of cool. And anyone who's looking at their image on their iPad or, computer or whatever can presumably do the same thing. There's M15. This one is special to my heart because I didn't have time to tell you about it, but in the summers between my sophomore and junior years in college, I worked as a guide at Lick Observatory, and I was allowed to use a 12-inch refractor, and I monitored RR Lyrae stars, which are like little versions of Cepheid variables. So this cluster is very dear to my heart. A bunch of these stars are RR Lyrae stars, but that's a 3-minute exposure. Just all of you know this, but globular cluster in the halo of our galaxy, open cluster in or near spiral arms, okay? Now here's a galaxy. There's M51, the Whirlpool galaxy, after 4 minutes. It's a low surface brightness galaxy. I mean, if you guys have looked at it at your star parties, it's not an easy target. It's like M101, another face-on galaxy. They're low surface brightness. They're not like Andromeda or something. But here are the arms, very nicely delineated, even some little spurs coming out. You can see some H2 regions, some Orion Nebula type things. The arm going out to the companion galaxy, which is helping to drive the spiral structure through a gravitational interaction. Here's NGC 891. Quite a hard target, folks. I've zoomed in so much that I can't tell what the exposure time is, but it's a couple of minutes, something like that. This one's an edge-on galaxy. Oh, I'm seeing Deanne. Blue Oyster doesn't show up. Sky Safari. NGC 1501. Yeah, Blue Oyster Nebula. NGC 1501. Thanks, Suresh. But here's NGC 891, a nice edge-on spiral galaxy, a really great contrast from the face-on M51. And I remember looking at this thing, and I had to sort of use my imagination and my knowledge to convince myself that I was seeing the dust lane. M104, the Sombrero galaxy, it's a lot easier to see through a telescope. But here, in a couple of minute exposure, you can see it very well. Here's the central part of the Andromeda galaxy. I see central part because this field of view is 1/2 degree. And as you know, in the deepest pictures, M31 takes up 3 degrees, 6 full moons. So this is showing the inner part, but here you can see some of the dust lanes. Andromeda is like, 27 degrees inclination, something, neither here nor there. So it's a bit of a boring galaxy to look at from my perspective, though critical in the history of astronomy and easy to look at, naked eye, from the suburbs of Minneapolis, I'm sure. There is one of its companions, M32. And I show this juxtaposition when I'm doing star parties for my students, showing how big Andromeda is. And M32 is at the same distance, but it's a dwarf galaxy, a dwarf elliptical, not a Magellantic irregular. And both of them have a black hole in the middle. So even the dwarf guys sometimes have a black hole. There's M81, Bode's galaxy. For some reason, didn't show up in the label here. Sometimes it does that, but many of you will recognize this coordinate. So that's M81, and then the cigar galaxy with which it's interacting. This kind of looks like an exploding galaxy, but that's because there's a lot of gas being ejected out from the massive young stars and the supernovae. So it's pretty incredible. Here's M65 and M66, a nice pair in Leo, where again, you can actually see the H2 regions, the, Orion Nebula type things, and the OB associations. And this looks like a barred spiral galaxy to me. So there's been, the Messier marathon is actually quite easy with the EV scope because it just goes zoop, 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 locks in on what you do. Oh, by the way, you set it up on its tripod and it's pointing straight up at first, but that's sort of a singular point. So use the little paddle control to just move it downward a few degrees. And then you hit a thing on here saying, basically identify the sky. And what it does is it identifies where it's looking. It has a catalog of all the stars in its memory. It says, I know where I am, field identified. Then you go to any one of a number of, thousands and thousands of objects in its database, or you can type in a coordinate and then you just say go. And it goes there, doesn't land right on it immediately, but lands near it, takes a picture, recognizes the star field, does a correction, takes another picture because the correction isn't quite right, recognizes the field, does one more correction, and then says, I'm locked on. And rarely do I need to use the hand paddles to center it. If I've done a good job making it level, and there's a little level bubble on this thing before you mount it. And there's like 2 screws. It's the easiest thing. I have it set up in my room right now. I just carry it outside. I take it off in order to look at where the bubble is, and then I just put it on. But then you're done. You tell it, recognize where I am, and then you're done for the night. It's amazing. And it tracks, not because it's an equatorial mount, but it's doing it all electronically. It's seeing the stars move, so it clocks out, it reads out the CMOS or whatever. I'm not exactly sure how it does it. It either clocks the charge along the pixels or it reads it out every 4 seconds or something. I'm not sure what it does. You can look at the thing, but the point is it builds up those images automatically. So anyway, it's amazing. And if you're into things like exoplanets or monitoring comets or asteroids, their amateur astronomers are monitoring these asteroids to help trace their orbital elements better to find the killer asteroid before they come, and especially for citizen science. So if you're interested, email this guy, Leo Ludwig, at leo.ludwig@unistellaroptics.com. Give him my name and this code, ALFI, I guess it's for Alex Filippenko, ALFI-493 JRM. I have no idea what this means, but they'll give you this discount. And now they didn't answer my email message today, but up until a few months ago, they were also giving people a jump of 1 month in the queue because there was a waiting list. Now that they've run out of EV scopes and they've started making the Equinox, I don't know what their queue is like. Maybe they're completely up to date. I'm not sure. But if they're not up to date, then I think that they'll give you a jump in the queue, but I'm not absolutely certain about that. But anyway, that is, I think, all I had. And it's kind of way over, but I talked too long, but I promised that I'd give a few more minutes. Oh yeah, it's a 4.5-inch telescope. Yeah, so it's like a Questar, and those are really expensive too. But a Questar doesn't give you the digital image that you can go and analyze or show in a Zoom session or whatever. M81, 9 hours. No, that was the right ascension. That was just a couple of minute exposure, I think. Actually, that one was 30 minutes, but it was nearly the same after 4 or 5. I think I got it all the way to 30 because I was answering a bunch of questions. This was the last object of the evening for some star party that I did on some date. What was the date? It was February 5th. Yeah. And then I thought, well, gee whiz, since I integrated for 30 minutes, might as well do it. But yeah, the right ascension of M81 is something like 9 hours, almost 10 hours. Yeah. Love the spiral arms. Yeah, I do too. But Yeah, so the most exposure I've usually done is like a few minutes. All right, let's see. Yeah, in the chat room, or if you want to just unmute yourself, as long as everyone doesn't do it at the same time, that would be fine as well. Let's see now. I saw, does the vacuum energy density vary over time? Okay, so if the vacuum energy density is the cosmological constant, then it doesn't change with time. But if it's something else, it could change with time. In the same way time is slowed near high mass, does the flow of time vary? Not really, because in a uniformly spread out, uniform density universe, time flows at the same rate. It's only near a black hole or near the Earth or whatever that you have to take that into account. And the inflationary period is in fact the historical precedent for thinking that the dark energy might change, because the inflationary period in the first blink of an eye was what inflated the universe to a gigantic size. But that stuff, the inflaton as it's called, the version of dark energy that existed at the beginning, it decayed into particles, antiparticles, and light. Then most of the particles and antiparticles annihilated each other, producing more light. But somehow a slight imbalance of matter over antimatter occurred, and that's why we're here. But it's this changing nature of the inflaton that is a historical precedent to the dark energy like substance changing with time, which is why I said that there's still a chance that it could become gravitationally attractive in the future and cause a big crunch. Yeah, let me just while you're there, let me just type something here. Let's see here. I wanted to type to, where's everyone? Well, oh, here it is. I could have typed it's Leo Ludwig, but let me also just type that in case you want to, but yeah. Other questions, anyone? Great.
Go for it.
Super.
I just had a question briefly. I'm just wondering about what is your personal thoughts as far as like the satellite constellation issues, how that's affecting either your research or ground-based astronomy as a whole, because I've been reading like a lot of the papers coming out and concerns about how it's affecting the overall darkness of the skies and new data and things like that.
Yeah. So it's a major concern for something like the Vera Rubin telescope, the 8-meter telescope that's being built in Chile, because that telescope is going to take wide-angle pictures of the sky that will get saturated. The CCDs will get saturated because of these bright things going through. So Elon Musk finally agrees that this will have some impact on astronomy. For a while, he was vehemently denying that it would do anything to us, but it will. And so they're trying to mitigate the problems by making the satellites darker, not as highly reflective. We want to get them below magnitude 6.5, preferably 7, but at least below 6.5, because at that magnitude, although the main streak of the satellite through images obtained for the LSST, the Large Synoptic Survey for Transient Objects, to be done with the Rubin Observatory, though the main thing will be saturated, there won't be the huge crosstalk that occurs among the different amplifiers. And so a much smaller fraction of the total field of view will be affected. When these things are first launched, they're like second magnitude. I've watched them. Maybe some of you have. For whatever reason, they're first placed in a relatively low orbit, and then they're boosted higher up. But when they're in their initial low orbit, really low, I mean, they're like second magnitude, and they're like pearls on a string. I've watched them go through Leo. And then, when they boost them up, they're like fourth. But that's still really bad for these wide angle surveys. So they're trying to mitigate the efforts, and we're hoping, or mitigate the problems, and we're hoping that other companies will as well. For my own research, where I study some supernova that has already been found either by my group or some other, it's not a major problem because I'm looking at a tiny field of view, getting a spectrum of a supernova or looking at a particular galaxy. You know, the odds that the satellite will go through my field of view are tiny, but the Vera Rubin telescope is going to have these gigantic fields of view with gigapixel cameras. And you've probably seen online, people have published some pictures of like up to 17 of these things going through even today's version, which is called the dark energy camera on the Cerro Tololo 4-meter Blanco telescope, the one we use to discover the distant supernovae. There's been some amazing images where they saw several going through. There's also been some fake images where people, they add together different images that had one satellite go through, and they make it look like 19 satellites go through. Well, that doesn't help our cause. If you start saying things that are not true, you know, then sure, Elon Musk will say, well, that'll never happen and blah, blah, blah. But so you don't want to overly exaggerate, right? You really don't want to exaggerate at all. You want to be completely truthful. But with the Vera Rubin telescope, that will happen, that sometimes there are multiple satellites, especially once there's like 100,000 of them up there in the sky at the same time. And I understand that they want to, you know, make internet available to the poor parts of the world and all that kind of stuff, you know. But we're hoping that they can, so we're never going to win completely, right? We're not going to say, well, the satellites will hurt astronomy, so don't send the satellites. There's no way we can win that. So at best, we can be respectful and talk to them and convince them with real data that this is an issue and work with them on ways to mitigate it, you know? Yeah. It says Musk owes the astronomy community a couple of fully paid space telescopes. Yeah. You know, you could imagine that if they didn't care and you over time had a bunch of second magnitude things flying around up there, they would start dominating over the visible constellations, right? So fortunately, that's not going to happen, you know, maybe from some dark site, right? You can see down to magnitude 6.5, and it's actually kind of fun. When I'm in a dark site, it's kind of fun to find satellites. You just don't want too many of them. Oh, Nicole says you went to my Kaufmanis lecture. That was, I was going to say decades ago. Wow, that's great. Were you at University of Minnesota, Nicole? That's wonderful. Wow, I'm going to take a screenshot of that comment there. So yeah, Ben Hussett. Yeah, I know that name. Who is Ben? For some reason, I know that name. Maybe not. Is that a member of your club?
Yes, it is.
Oh, okay.
Yes, it is.
Santa and his reindeer. Right. Because if you've seen some of these things shortly after launch, they're like in a row. And maybe the front one isn't the brightest, but you know, I don't know that Santa had a brighter light bulb than any of his reindeer, right? But yeah, Santa and his reindeer. I love that. Any thoughts as to what the future direction or discoveries for astronomy? Yeah, well, in the past 5 or 6 years, of course, gravitational waves have been the big thing. So that's really cool. I think, you know, in the next 5 or 10 years, we could discover Earth-like atmospheres in the, you know, around some exoplanets, maybe not with oxygen plus methane, not, you know, necessarily with a great biosignature, but at least atmospheres that might make the exoplanets look like Earth's, not just in their mass and their distance from the star, but maybe even in terms of their atmosphere. That would be pretty cool. And what would be really great is, you know, biosignatures of life. That would be pretty cool.
Well,
you know,
Alex.
Yeah, go ahead. Mm-hmm.
Well, Alex, I don't want to take up all of your night.
Okay, sure, yeah.
So I want to thank you very much for your time tonight. You've been very, very generous. You know, we did talk about just 90 minutes, and look at this, it's already over 2 hours.
Right.
Thank you very much. We really appreciate it. And, you know, maybe if there's some really interesting questions, we can send those to you by email, and maybe we get a response and we can share those later.
Yeah, we'll see how it goes.
Yeah, exactly. So thank you very much for your time.
And I'll just put this, where was it? I don't even know if it's there. If you, let's see, it's right here. Yeah, if you wanted that Leo's thing, there it is, one more time. But thank you so much. You've been a great group and really awesome set of questions. So, okay.
You've been very generous. Thank you very much.
All right, bye-bye.
Yep, you bet.
Bye-bye.
Thank you. Bye-bye.
Okay.
Well, see you next month.